Chanda Devnath, one of the PMRS fellows. So I am pursuing my PhD from IISER Berhampur. Right now I'm a TA of this course. I am TA of this course, Mechanisms in Organic Chemistry. Here we will discuss usually some concept about this topic and also questions based on that. So let's start. So in the last class we were discussing about secondary kinetic isotopic effect. Then we solved some questions based on that. After that we started isotope leveling and then we started intermediate trapping and also solved some questions based on that. So I am carrying forward this. Before that I gave a homework or a problem to try by yourself. So I hope everyone has tried to attempt that. So today I will solve this one. So what they asked, so I will just solve this one, then we will start today's class. So they asked, so these two reactions of diazo compounds with carboxylic acid give gaseous nitrogen and esters as product. In both of the cases, the rate of the reaction is proportional to diazo compound and acid, and use the data for each of the reactions, suggest mechanism and comment on the difference between them. So what they are asking here, they have shown two types of reaction where the product is almost the same and they gave the Kh by Kd value for both of them. And asked for the mechanism. Now if you see in the first case, you have to notice that they have given the values in a very tricky way. In the first case they gave a Kh Kh by Kd value, whereas in this case they gave a Kd by Kh value. See, so if we are just seeing the value and we will go to solve this question, there will be a mistake because they have done a tricky way. They just switched the pattern. Now if we just make it like this way, usually whenever any kinetic isotope effect is given, that is given as a Kh by Kd value, not Kd by Kh, because we know Kh by Kd greater than was is faster kinetic primary kinetic isotope effect. So this will be to compare that it is to know if that this is a primary kinetic isotope effect or not. We have to get the Kh by Kd value. So we will just switch it. So this will be our Kh by Kd value for this reaction, which is obviously less than 1. So from this one we have what we can say, that for this one that it will not show primary kinetic isotope effect. So it will not show a primary kinetic isotope effect, because in the previous classes we have talked about this one, that to show primary kinetic isotope effect, the Kh by Kd value should be greater than 1. And what does it mean? That means our hydrogen bond, the CH bond is getting broken, or the hydrogen bond is getting broken at the rate determining state. So here in the second reaction, the hydrogen bond will not break in the rate determining state, whereas in this case the OH bond of this acid, because they have compared the rate with respect to carboxylic acid. See, they just change the hydrogen of the carboxylic acid. So here the OH, not the CH. So here in this case, the OH bond will break at the rate determining state, while in this case it will not break at the rate determining state. So if we just go through the mechanism, what we will get? See, in this case, first the diazo compound from this position, so what is happening? This negative charge is coming here, and by this pi bond is taking this proton from this carboxylic acid and making a carboxylate anion. So this step in this case, in the first case, is a rate determining step. So the hydrogen bond is getting lost at the OH bond is breaking at the rate determining step. So that's why it's showing a primary kinetic isotope effect. After that, it's making positively charged a leaving group, then N2 will leave from the system generating a carbocation, and then again it will attack to this carbocation forming this ester moiety. Now how we can get an idea that this reaction will go through this pathway, that first this hydrogen will take up and a carboxylate anion will form. That we will get idea from this rho value that we have discussed in the earlier, I think 2-3 class before, the Hammett equation. From Hammett principle, you know that whenever the rho value is a positive value, whenever the rho value is a greater than 1, a positive value, that means the reaction going through a carbanion intermediate, that or maybe a carboxylate anion intermediate. So reaction will go through a carboxylate anion intermediate, that is sure. So here a carboxylate anion intermediate is forming. And from this one we are getting idea that the carboxylate anion intermediate will form, and from this Kh by Kd value you can get an idea that which step will be a rate determining step. So in this case, this first step will be the rate determining step, whereas the similar type of reaction will happen in this case. First the proton abstraction, after that the carboxylate anion will attack to this electrophilic center, and it will get removed and forming this ester moiety. But in this case, as the carbocation where it is generated, this carbocation is not stable. If we go through the upper one, like the upper one, we are just removing the N2 and generating this type of carbocation. See, this carbocation is not stable because just adjacent to the carbocation there is a very electron withdrawing group ester, which is show -I and -RFA. And because of that, this carbocation is not stable, which makes this carbocation formation is not feasible. That's why this reaction goes through a SN2 pathway. And make this step as a rate determining step. Because of that, here you can see the hydrogen bond breaking, the OH bond breaking. Here the H plus is coming from this carboxylic acid. They have just, in this case they didn't draw the carboxylic acid. This H plus is coming from the carboxylic acid only. So now in this case, the first step is the fast step. Fast, like the first ever step is the fast step, not the rate determining step. In this case, the very first stage is the rate determining step. So you have understood the mechanism. So now how can we determine that when it will be the rate? You can determine from the H by Kd value and also the rho value, and if you can go through a just normal structural isomer, you can see that in this case there is a aryl group present adjacent to this electrophilic center, which makes the first step, this carbocation formation step feasible, and make this step as a rate determining step. Whereas due to this electron withdrawing effect of this CO2 group, the carbocation formation step is not feasible. That's why this reaction goes through a SN2 pathway and make the second step as a rate determining step. Understood? So how we are determining which one is the rate determining? Based on this Kh by Kd value. As the first one is showing the primary kinetic acidity effect, so first one is our rate determining step, and the second one is our, in the second case, the second step is the rate determining step. Okay, I hope it's clear. Let's go to our next topic for today. While we discuss, in the previous week already started about trapping reaction. So trapping, intermediate trapping. So what is intermediate trapping? So intermediate trapping, to determine the nature of an intermediate, we can trap the intermediate by some other group, that is called trapping. Suppose you have a, this trapping can be different type of, like if your intermediate is anion, that can be trapped by a electrophilic basis, because the intermediate, if the intermediate is anion, that is already electron rich. So to trap that, you need something which has a scarcity of electrons, so that can take electron from that anion and get a and form a compound. So to trap an anion, you need a electrophile. Whereas to trap a cation, you need a electron efficient compound. That is, to trap a cation, you need a nucleophilic center. You need a nucleophilic compound. Now, in some cases, the reaction intermediate is a radical. So to trap a radical, we sometimes need a different type of radical trapping reagent that we will discuss after that. You can show the some spin trap like nitroso or nitron. For that, if a radical is in and to suppose, we will discuss later. I think by example it will be easier to understand. So first we will discuss about anion trapping. So how anions can be trapped? Now suppose this enolate intermediate. Suppose this enolate, you know about this enolate intermediate. This is one of the important anionic intermediate. So if there is an acidic H adjacent to a carbonyl group that is highly acidic because of this resonance effect, the minus I and minus R effect of this two ester moiety, minus I and minus R effect. So this alpha hydrogen is highly acidic, and due to that you can take this alpha hydrogen by using any base and create a negative charge on this carbon. This negative charge can be stabilized by this adjacent carbonyl . By this adjacent carbonyl moiety. So if instead of ester there can be different type of electron withdrawing group. Here is the decreasing order of this electron withdrawing ability of this group. Now this type of enolate, how scientists determine this enolate has in a reaction. How can I determine in a reaction this type of enolate intermediate is forming? Easily, just by trapping it. So enolate intermediate is a negatively charged intermediate. So enolate intermediate, this is called enolate intermediate. This is called enolate intermediate. So this enolate type of intermediate is negatively charged, because how it will react? If this will come here and this it will react from this carbon. So this type of enolate intermediate is negatively charged, and we know to trap anion we need a electrophile. So suppose I have shown some of the example. So here we have given this type of cyclohexanone type of ring. Now if we are adding LDA, then what will happen in presence of LDA? This hydrogen is more acidic, because in this case there is a methyl group present there, so it has a plus I effect. So in this case this hydrogen is more acidic, so it can be trapped very easily, and this will comes here and it opens up, forming this enolate. LDA is a base. LDA is a very strong base. These are common bases which we use in laboratory. So LDA is a base. So how now this, if this type of electrophilic center is given, so this will come here and it will attack from this carbon to this electrophilic center, and bromine will get removed from the system, and we will get this one as our only product. So in this way you can trap a enolate. Just by adding a electrophile we can trap the enolate intermediate. So in this case this reaction is going through the formation of this intermediate is proved now, because other than any other way we can't get this product. So if we are adding any base to this type of substrate, what we will get? We will get this intermediate. This is proved just by adding a electrophile. That electrophile is trapping this anion or this enolate intermediate, and from that we are getting an idea that this enolate intermediate is forming. So this is a similar type of reaction. Now what will happen? This is among these two, which one is more acidic? This hydrogen, because this hydrogen has plus I effect of these two methyl. So this hydrogen is more acidic. Therefore it will take up this hydrogen and form a simple enolate. I am just drawing the cyclohexane as an art for simplicity. What will happen? This enolate will attack to this another aldehyde which is given. This will open up. This is acting as electrophilic center, and we are getting this product. This reaction, this type of reaction has a specific name which is called aldol reaction. You have all know, I think, about this aldol reaction. This type of reaction is whenever there is a ketone or aldehyde with the alpha hydrogen and we are adding base, that alpha hydrogen will take up and that negative will attack another aldehyde or ketone if present in the reaction medium and form this type of beta hydroxy ketone. This type of reaction is called aldol reaction. We can use this concept for halogenation also. If we add a halogen as an electrophilic group, we can add halogen at the alpha carbon to the carbonyl moiety. So based on this concept, this enolate trapping concept or this enolate type of by using this type of enolate intermediate, we can perform different type of reaction. So by using this type of enolate intermediate, we will perform, if you know, now if some substrate is given and you know in presence of base that will form an enolate intermediate, that will be easier for you now. If you know that which type of substrate will form which type of intermediate, then it will be easier for you to perform a reaction. Okay, so how it will behave in a reaction medium, that you can know now. So based on that, one question came in GATE 2021. So what they asked, they have given this substrate and gave LDA. LDA, you know, LDA is a base. LDA is a base. And they given this P6BN, which is a electrophile. Because bromine is here and can be removed easily from the system. So this is a electrophilic center. This is a electrophile. Okay. So what will happen in this case? Very simply, in presence of LDA, in this case there is no such competition because only one side has alpha each. So this will go here and form a enolate. Now what will happen when you are adding this electrophile, like previous reaction, this will go comes here and from this carbon center it will attack to this electrophilic center and remove this bromine atom from the system. Okay, so what will form? So what will form? Now, what is the role of this adjacent group? See, so whenever this double bond is attacking to this electrophile will approach to this center. This electrophile will approach to this center. Now, there is a very bulky group adjacent to that, and it has a above the plane group which is quite bulky, isopropyl group in itself. So whenever there is a bulky group above the plane, so it is very difficult for another group to come from that plane. So it will try to come from the opposite plane. So here, as this group is in the above the plane, so upcoming electrophile will enter below the plane, from below the plane. The upcoming group will enter from the below the plane. Suppose this is a 3D, this part is planar, this part is planar. Now this, just imagine this isopropyl group is above the plane, just like a tree. Suppose this is your field, okay. Now this is tree, this is like a tree. On a field, this is like a tree. Now if something wants to come, suppose something wants to come on the field. Now this tree will resist. This is a big tree because there's a methyl, 2 methyl group. This 2 methyl has 3H. So this is like 3H atoms are here. So the very large group. So anything which wants to come from this above plane, which feels a huge strain with this isopropyl group, that's why that will come just opposite side of this group. It will come from the below the plane. Now the next reagent, what they add LiLH4. What will do? This LiLH4 will break this amide bond. In presence of LiLH4, this amide bond will break, forming aldehyde. First, LiLH4 means hydride donor. LiLH4 means hydride donor. That will attack here and it will break this amide bond. Now LiLH4 is so strong and it's still in the medium, because after one hydride attack you can't remove the product from the system. This LiLH4 is still in the RB. LiLH4 is still in the RB. So what it will do? It will attack again to this aldehyde center, because LiLH4 is still in the medium. It's attacking because suppose LiLH4 is added in excess, 3 equivalent. If it is compound is 1, the LiLH4 is added 3 times much than that of our substrate. So one equivalent has been used in the first case, but still in the medium 2 equivalent of LiLH4 is still there. So that's why that will attack to this aldehyde center and it will open and form aldehyde. Under reduction with LiLH4 forms alcohol and from this product. So which one is our correct answer? Option A. Okay, I hope it's clear. Let's go to our next question. So what they asked, suggest a mechanism for this reaction and comment on the relevance with the Favosky family reaction. So whenever now this double bond is given and there is a bromine, so you know whenever on a double bond, if bromine is given, what will it will undergo a tribromination. Form a bromonium ion. Will form a bromonium ion, and that bromonium ion from this tribromo compound. From this tribromo compound. After that, when we are adding a base in the system, what will happen? So now see, this bromine center is a 3 degree. After removal, there will be possibility of carbocation formation, or and there now is a carbonyl compound with the alpha hydrogen. There is a alpha hydrogen present. So in presence of base, what will form? Whenever there is a carbonyl compound with the alpha hydrogen and base is added, I have told in the previous slide what will it will form? It will form a enolate intermediate. It will form a enolate intermediate. So it's forming a, so this proton comes here and it forms a enolate intermediate. This is a enolate intermediate. Now this enolate intermediate will undergoes. Now suppose to trap an enolate intermediate, we usually gives a electrophilic center or a electrophile to the reaction to trap that enolate intermediate. Suppose a substrate has an electrophile inside it. If you want to eat something, we go outside and eat food. Suppose you have already that item in your home, then you will eat from whatever you are getting from your own place, right? Because that will be easier for you. This compound will go to other and attack to another compound. That is quite difficult because it has to go to close to another compound, then it will attack. That is a very big, very much work to do. But if it has own electrophilic center, what you will do? It will attack to itself. So this center has a high electrophilic property because the bromine atom is attached, and this is highly electrophilic by this minus conjugation with this carbonyl compound. So that's why this will remove from the system, generating a positive charge, and that will comes from at this place and forming this intermediate. Forming this intermediate. This is called this step is called Fabovsky reaction. Now in the reaction, base is still there, so this base will come and attack to this and open this one. Then again this O minus will come and open. And now this is a highly strained ring because 5-member and 3-member fused ring. So this will open up, break this 3-member ring and form our desired compound and remove another bromine from the system and form our desired Zeta. I hope everyone this is clear because Fabovsky is a famous reaction. I think most of you have read about it. If not, then you can go and check on Google. Just write Fabovsky reaction. You can get the general mechanism of that, and you can relate how it's related to the Fabovsky type of reaction. Okay, so to trap an anion or enolate anion, we will just have to add a electrophile. If the compound is not getting electrophile from the outside and there is a electrophilic center inside itself, then it will attack. That will undergoes a intramolecular electrophilic addition. Okay. So there is a question. You have to draw the mechanism. I think you guys can try it by yourself. See, this has also alpha hydrogen and alpha bromine. Whenever there is an alpha bromine center, what we have done? We have done a Fabovsky type of reaction. Alpha bromine and with the alpha hydrogen. Whenever there is a ketone compound, with the alpha hydrogen in one side and alpha leaving group in another side, that undergoes Fabovsky type of reaction. Usually in presence of base, that undergoes a Fabovsky type of reaction. Now in this case, you see there is a alpha hydrogen from this methyl, is alpha bromine also. So we can perform a Fabovsky type of reaction. So it's a hint. First try by yourself. I hope you will get the mechanism very easily. Okay. Next is carbocation trapping. So what we will do to trap a carbocation? Similarly, to trap a carbon ion, what we have done? We have just added a electrophile. So to trap a carbocation, what we will do? We will just add a nucleophile. So suppose this type of reaction is given. how we are getting this product. How we are getting this product. Now what will happen? This is the leaving group that will remove from the system. Okay. Now there is a methyl and a hydrogen atom. And this carbocation is 2 degree. So if we just shift this hydrogen atom, hydride shift, what it will form? It will generate a carbocation at this place. Now this carbocation is 3 degree. As well as the one another new factor is that there is an adjacent triple bond. Now this type of triple bond usually behaves as a double bond. This resembles the role of a double bond because the high overlapping of this p orbital, there is a three carbons are sp3, so it has a this sp3 orbitals has a close overlapping. So this because of this close overlapping of this orbital, this type of triple cyclopropane ring behaves as a double bond, behaves as a similar to this alkene compound. So now we know whenever this alkene type of compound is given that has a allylic stability, this double bond can stabilize this carbocation. Similar type of stability at this place. So there is a allylic stability. There is a allylic stability because triple cyclopropane ring behaves as a double bond. Cyclopropane ring behaves as a double bond. There is a allylic stability, and after that what will happen? There is a ethanol is given, so ethanol can act as a living nucleophile, and that nucleophile. So to know, so by this one, now in our reaction, how can we know that reaction is not going from this electrophile but this electrophile? Just add a nucleophile. Just add a nucleophile. That nucleophile will trap this carbocation, and from that whatever product we will get, if that resembles with our expected carbocation, then it is going from that carbocation. If it's not, then it's going from another type of carbocation. So here what we are shifting? We are shifting a hydride shift is taking place. So from this reaction, what we are gaining the knowledge? From this reaction we are gaining a knowledge that to know which type of electrophile is forming. Some of you can predict that okay, the reaction is going to the just leaving group will remove, then 2 degree radical will 2 degree carbocation will form, and there will be just a nucleophilic addition. But whatever product we will get will not resemble with the product actually we get. In this case we will get actual product, this one. So from that one we can get an idea that reaction is going from this type of carbocation. In a chemistry, whenever we will just get the product and give an explanation of that. So we are just getting this trapped product, and based on that we are giving this explanation that this carbocation is forming. Okay. So by this one we are just trapping this carbocation. Now there is another reaction is given. What will be the product of this one? So this is called as a Beckmann cyclization reaction. This is called as a Beckmann type reaction. In case of this, now suppose this bond breaks. Now suppose if this bond breaks, what will happen? The carbocation will generate at this place. Now if this bond breaks, carbocation generate at this place. So which one is more stable? If a electrophilic center on a benzene ring is not stable because this is sp2 hybridized, and carbocation a positive charge on a benzene ring is not stable. So which will go? The reaction will go through this pathway, not this one. So what will happen? So this will generate, there is a CN center will generate C triple bond N. An electrophilic center. Now to trap this electrophile, suppose now see here ethanol was given, but here no such nucleophilic center is given. So as we have discussed in case of phenolate, if there is no such electrophilic or nucleophilic center given for the reaction, but it has a electrophilic center inside itself, there is an electrophilic center or nucleophilic center, it will go react with that one. So this compound has an electrophilic center in itself, so that will react, and the compound has a nucleophilic center in itself, which is this pi bond. So it will react. So this pi bond, from this pi bond it will attack here, and from this type of thing through aromatization we will get this product. Okay, so we have talked about anion trapping, carbanion trapping, carbocation trapping. So for carbanion trapping we will just add electrophile, to carbocation trapping we will just nucleophile. If there is no such nucleophile is given, and but our intramolecular nucleophilic center is there like a pi bond, that will attack and neutralize our desired compound. Next is radical trapping. So to trap a radical and to turn into a stable radical so that we can detect it from APR spectroscopy, we usually use this type of stable radical. Why this is stable? Because of high bulkiness, this type of radical can't undergoes a homocoupling reaction, that this one molecule of this radical cannot couple with another molecule of this radical. So as a radical they are very stable, it can be bought and stored in under cold temperature. In fridge you can store it very easily. In laboratory this type of compounds are usually there. To know that a reaction is going through a radical or not, if you are adding this type of reagent, then you will get, suppose a reaction is this one. Now we want to know this reaction is going through a R plus, R minus or R radical. How can you know that? To know this one is very easy pathway, that if you are adding a nucleophile, if any reaction perform and that traps this electrophile and form a compound with this nucleophile, then the reaction is going through a positive pathway. If you are adding a electrophile and that gets trapped, then reaction is going through a R minus intermediate. But if we add any of this compound, suppose one is this, if we are naming is at A, if A is given and by coordination we are getting Then from this one we can get an idea that reaction is going through a radical pathway because it undergoes a radical coupling. So from this one we can determine that reaction is going through a radical pathway. Now one reaction is given, so you have to draw the mechanism. So whenever TiCl3 is given to a aldehyde, titanium, zinc and copper, it forms a titanium radical. That radical will attack to this carbonyl center and form a O radical. So it will form this type of O radical. There is another carbonyl that will also form a O radical. Now what will happen? Now if, as we said in case of electrophile nucleophile, if there is no such trapping reagent is given and there is a probability to trap by itself, there is another trapping reagent inside it, it can trap that. So there are two radicals are given, so they undergoes a coupling reaction and form this type of we get this one as our product. We get this one. So there is undergoes a internal coupling. And forms this type of carbon-carbon bond. Just by taking proton, we can get our desired product. Okay. So for radical also, if there is no such radical compound is given to the product, to the substrate, then what if it has another radical center inside itself, that will undergo the radical coupling and form our desired product. So for electrophile, nucleophile and radical, for all these three cases, you can now easily solve a question. So this is another question. I think you guys should try this. I'll just give 5 seconds. For the idea, I'll just give a how this reagents will behave. This AIBA means is this type of reagent which undergoes a homolytic coupling and form this two type radical and this N2 get removed. Now this radical can take a proton from this tin complex and form this radical tin complex. Now that will react with our substrate. So try to guess what will form. I just gave an idea how the reagent will behave. Now this will react with our substrate. This will react with our substrate. How is this? How it will react? Just try to get that. I'm just giving 5 seconds. What it will do? This tin radical has a high to attract this halogen moiety and form this type of radical in the system. Form this type of radical in the system. Now to trap this radical, we have to add some reagent which will trap this radical. So what is other radical that can trap this reagent? So there is because after taking one, this radical will form. Now suppose instead of this CN radical, this radical itself taking up this proton and forming this tin. And what will get? Is forming this radical. Now this radical is taking proton from this tin itself and form our desired product. Okay, I think it's clear. Our next intermediate which we will discuss today, that is benzyl intermediate. So how we know that in a reaction benzyl intermediate is forming? So benzyl is a highly reactive intermediate. Right now recently the benzyl chemistry has been very famous. Some scientists are recently working on this chemistry. So benzyl is a highly reactive intermediate with a distinctive structure featuring a benzene ring with a triple bond. Is crucial in nucleophilic aromatic substitution and Diels-Alder reaction. Understanding the benzyne's reactivity aids in synthesizing complex organic compounds and offers educational insights into the reaction mechanism. So how these benzynes can be formed? Is another possibility. Where if we are forming a Grignard moiety, then this negative Grignard has a partial negative charge as this carbon. So this negative charge will come here and remove the fluorine from the system. We can get a benzene. Then just by coupling two alkyne with the alkyne system, we can get this benzene compound. There is another different type of possibility by which we can form this benzene. Here I have shown all of them. This is the one which I showed just recently. There is another probability just by if it comes here and this N2 will remove from the system. some different probabilities there. If OTS this becomes here. In this different pathway you can form benzene in our reaction mixture. Now how you can get an idea that benzene is forming? Just by trapping it. Now suppose this type of reaction is given. Just by adding HONO, we know that what it will form? It will form a diazo compound. NaNO2HCl will form a diazotization of this amine. This is a diazotization reagent that we know, I think you have learned about in your preliminary classes. This is a diazotization reagent. So whenever there is a diazotization reagent is given and a primary amine is there, it will form a diazo compound. So it will form now here you can see a diazo compound with a carboxylic acid adjacent to that form a benzene. So here similar type of reaction will take place. So this comes here. This gets removed from the system, forming a benzene intermediate. Now to trap this benzene intermediate, this can act as a, yes, in the previous slide we discussed that it acts as a very good dienophile for Diels-Alder reaction. So there is a diene in our system. Inside the system there is a diene. Inside our system there is a diene. So this diene will undergo the Diels-Alder type of reaction, giving us our desired product. Okay? Understood? I hope it's clear. Let's go to our next question. So here also they have given a diazotization reaction. So what will form? It will form a diazo compound. This will comes here. Forming a benzene. Now this benzene will react with one of these double bonds. So suppose if this is already aromatic, so this will not react. Now if among these two diene, one of them will react. Now suppose if this one reacts, there is a double bond comes here. there is a quality double bond comes here. Sorry, this one is the quality of double bond coming here. So that will not give any extra stability to the compound. But these two double bond react, then it will give a double bond at this place. Just imagine Diels-Alder reaction. Whenever this diene reacts, there is a double bond comes at this place. So this giving a extra stability to this ring, because this ring is gaining aromaticity. So this ring is getting aromatic nature. So this will react to this diene. So among these three rings, the middle diene will react and our desired product is so there will be double bond at this place. From these two center, another double benzene, that is phenyl ring, will be connected. So here, if we try to draw which are the new bond formed in this reaction, so this is the new bond formed, and these two sigma bonds are new. These two sigma bonds are new, and this pi bond is new. Okay. So just by adding this type of trapping reagent, you can trap the benzene. So here is another. So if we are adding a base in this type of moiety, what will form? There is a hydrogen is available. So this NH2 will take this hydrogen, and this will comes here, move from the system, forming this benzene. Now to trap this benzene, what we can add? There is already living a nucleophile present in the system. So this nucleophile can attack from this place or this place. So if we attack from this place, it will open and give a negative charge at this adjacent to the OMe group. Whereas in the first case, what you would get? You would get this one as a product. Now, in the first case, the negative charge is adjacent to OMe group. Now, OMe has a minus I effect. OMe has a minus I effect. So, it can stabilize this negative charge, whereas it is far from the OMe. Minus I effect is dependent on the distance. So, here as it is far, so it will be less effective. So, here the product will be this one. So, this intermediate is more stable, and if we are adding H plus, it will take H plus from amine anisole. This will be our desired product. Okay. Okay. I hope it's clear. Next. So next topic we'll discuss about is types of catalysis. So there are different type of catalysis like acid-base catalysis, stain and distortion catalysis, binding, covalent catalysis, electrophilic catalysis, phase transfer catalysis, and nucleophilic catalysis. So first, today in this class we will discuss about acid-base catalysis. So understanding the acid-base equilibrium, if in an acid we are adding a base, what it will form? It will form a conjugate base and a conjugate acid. If we mix an acid and a base, this base will take up proton from this acid and form conjugate acid, and it will form leaving a conjugate base. Now if we are adding this acid into a water is a neutral compound. It has both the property acidic and basic property in a similar amount. So if we are adding acid into a base, into a water, if in presence of acid, water behaves as a base. In presence of acid, water behaves as a base. So what it will do? It will take proton from the acid, forming this conjugate acid and leaving this conjugate base in. Now in presence of base, water acts as a acid. Water acts as a acid. In this case, this base will take a proton from the water and form this conjugate acid, leaving this conjugate base in the system. Okay, I think it's clear. It's very simple. Now suppose in a reaction which is catalyzed by a acid. So in this case, this acid will give a proton. Our substrate will take a proton from the acid, forming this conjugate acid, and this conjugate acid will form our product. This conjugate acid will turn into our product. Now suppose, so if we draw the equilibrium of the reaction, what we will get? K equilibrium equals to RH plus into A minus divided by R into HA. And if we try to draw, and if we just take this RH plus at this place and take all the R, move all the R and this part at this place and A minus to at lower, then we can form the RH concentration. We can get this one as our value. Now the rate of the reaction, which is dP by dt, the formation of the product, depends on the concentration of this intermediate. The rate of the reaction depends on the concentration of this intermediate. So from this one we can get a concentration of this one, and just by multiplying it we can get our desired equation. From this one we can get an idea that reaction is dependent on the pH of the reaction. So the rate of the reaction depends on the P. From the equation we can get an idea that the rate of the reaction is dependent on the pH of the reaction, because the rate of the reaction depends on the concentration of the H3O plus which is gaining from the acid, H3O plus which is gaining from the acid. So from that we can get an idea the reaction is dependent on pH of the reaction. Now suppose the reaction is specifically base catalyzed. The reaction is specifically base catalyzed. Now suppose in a reaction you are adding a base. So what it will form? It will take the proton from the substrate. It will take a proton from the substrate, forming this carbonyl intermediate. This carbonyl intermediate turns to our product, and after that taking proton back from the base we will get our desired product. Now in this case the rate of the reaction will be like this. Here you can see the reaction is inversely proportional with the pH. The reaction is inversely proportional with the pH. That means with enhancement of the pH, reaction rate would be slower. Now suppose a reaction is there. Now variation of the rate of the ester hydrolysis with pH. So you have to draw the variation of the rate of the ester hydrolysis with pH. Now we can see the ester hydrolysis means one probability is in presence of base, that is OH minus. What will happen? This OH minus will attack here and remove the OR, forming acid as our desired product. So this is the mechanism of base catalyzed. Now another probability is if the reaction is acid catalyzed. So what will happen in case of acid catalyzed? This will get protonated. Then water molecule attack here and open up, forming this one. This will comes here. This will comes here and it removes from the system by taking this proton. And we get the same product. Now from this one you can get an idea that reaction is feasible in presence of acid, reaction is feasible in presence of base. Now pH means lower pH, pH less than 7 means that is acidic, and pH greater than 7 means basic. Now this reaction is feasible in both acid and base. This reaction is feasible in both acid and base, but the reaction is not feasible at neutral. The reaction is not feasible at neutral pH. So what will be the graph? So you can see with enhancement of the pH, if we enhance the pH, that means it's going from 0 to 7. As much as it enhance the pH, it goes to the neutralization point. So it's reducing the acidity. We are enhancing the pH, that means it reducing the acidity. So as the reducing the acidity, so the rate of the reaction will fall. Rate of the reaction will be slower. Now after 7 is again, if we are moving towards 14, that means it increasing. Now there is no such acidity remaining. After 7 there is no such acidity remaining, but in whatever the property is basicity. So now it enhancing the basicity of the reaction mixture. So as much as basicity increases, the rate of the reaction increases, so it will be the graph of the reaction. So for its ester hydrolysis, the reaction is feasible in acid and base, but its reaction is not feasible at neutral pH. So as much as the pH enhances, first the rate will fall. After just the neutralization point, then the reaction starts to enhance its rate. So it will be the graph of this type of reaction. So you can get an idea from that one. So if any reaction is given which is specifically catalyzed by acid, then which part of the graph you will show? You will just show the first part of the graph. If any reaction is catalyzed by only acid, then which type of graph you will see? You will see just the first part of the graph, that is this part. You will just keep this part of the graph. Okay. Now if any reaction is given which is just catalyzed by base, then you will just keep this part of the graph. Okay, understood? I hope it's clear. Now there are some examples of acid catalyzed reaction which is specifically catalyzed by acid only. This is epoxide cleavage. If you are adding acid to epoxide, what it will take a proton from the acid, then it will undergo the cleavage, forming this type of trans 1,2 diol. So epoxide are reactive to opening due to ring strain. After protonation, opening is SN2 like reaction, desire to relieve the ring strain and good electrophiles, because its 3-member rings are highly sterically strainful ring. Now another example of acid catalyzed reaction is this ester ether formation reaction. Ether formation by acid catalyzed dehydration reaction. If you are just adding acid to a alcohol, it will just take a proton from this one, then another molecule of alcohol will attack to this center and remove this OH from the system, forming this ether compound. Okay, these two reactions are specifically acid catalyzed. So for these two reactions, what type of graph you will see? If we draw log of rate versus pH, what type of graph you will see? Because these are acid catalyzed, if you are going from 0 to 7, the acidity will decrease. As much as acidity will decrease, the rate will also decrease. So for this one, we will show this type of graph. For this one, we will just get this type of graph for rate of the reaction. So now based on that, I have given two examples. So these are acid catalyzed. Because from the reaction you can also see they have given H2SO4. So this will be acid catalyzed. So what will be the product formed for these two reactions? So acid catalyzed will undergo what type of cleavage I have shown. So what we will do? Just try. I just give 5 seconds. Then I will solve it. So here this oxygen will take a proton from this acid from forming this now there is no such nucleophile is given, but a mild heat is given. As no nucleophile is given but if heat is given, so that means the reaction will undergo elimination, not substitution, because there is no such nucleophile is given. So what will first this will break, forming this 3-degree carbocation which is stable. This 3-degree carbocation which is highly stable. Now there is a proton which will comes here. Forming this alkene moiety. Okay. Now suppose this epoxide is given, that will also take a proton from this system, forming this protonated H plus. So epoxide undergoes a ring opening reaction that we have known in the previous case. It will undergo the ring opening reaction. Now which side it will break? From this side or this side? So if we break from this side, it will form a carbocation center at this position which is 3 degree. But if we break from this side, the carbocation center will be this position which is 1 degree. So it will always prefer to break from this position. It will always prefer to break from this position. Now in our system already methanol is given, so it will undergo a nucleophilic addition. Forming this as a desired product. Okay, I hope it's clear. So this much for today's class. So I will just give an overview what we discussed today. So first we discussed about enolate intermediate and how to trap it, and we discussed some questions based on that. This one given as a homework, so try by yourself. Try to do this one. I hope it will make a clear concept for yourself. Then we discussed about carbocation trapping and how you can trap this carbocation and solve some question based on that. We talked about radical trapping, solve some questions. Then after that we talk about benzene intermediate and how we can trap that. Then we talk about catalysis, different type of catalysis, acid and base catalysis, and if a reaction is catalyzed by both acid and bases, how the graph will look like, and if a reaction is only catalyzed by acid, how the graph will look like. We will continue this one in our next class, where we will discuss other type of catalysis. So thank you for today. I hope it was helpful for you. You can if you liking these classes, you can go and check my other classes also. NPTEL has provided the link, and all those videos have been uploaded in YouTube also. So thank you everyone. Have a nice day.